Welcome everyone. Here is the program for today. We will conclude the chapter on link state routing, or SPF. We will start congestion control, and tomorrow we meet again for a test. The program of the test does not include congestion control. We have seen everything we need to know, at least for the lab, about OSPF. Now I will discuss a few other things. In particular, in this section, we will discuss things that are not nicely following the layer that we have seen for the internet, but that are very symptomatic of how networking evolves. Link state routing, like OSPF, practically there's two protocols that implement link state routing, OSPF and IS-to-IS. Can be used, as we have seen it, and as we will use it in the lab, to compute shortest paths from a source to a destination. But it can be used for a number of other things, because, for example, once you have inside an area a complete view of the area, you can start doing all kinds of optimizations. One of them is called multi-class routing. Instead of computing one route for a given destination, or a few equal cost routes, you could decide on different routes depending on the type of traffic. In a very innocent way, it could be because real-time audio traffic into telephony or improved telephony requires very low delay. So you want to keep the low delay links for that kind of traffic. Perhaps for video streaming, you need a lot of capacity, but very low delay might not be so important. So you may decide to route different types of traffic according to different paths. You can easily do that with OSPF if you add other attributes to the links, not just their cost, but also some information about their delay, for example, or about how appropriate they are for some types of traffic. In practice, providers do even worse things. That you can decide that YouTube traffic receives a preferential treatment because you are the network of Google, and that other traffic perhaps has a different type of treatment. Let's see an example where link state routing can be used in a completely different setup. This is an illustration of what we have at EPFL for the Wi-Fi network. The Wi-Fi network has more than 1,000 base stations. And when you enter EPFL one morning, you automatically become associated with one virtual LAN, which is the virtual LAN that is natively associated with one given base station. Then as you move at EPFL, the virtual LAN moves with you. So we could have on a large campus, for example, 3 virtual LANs that happen to be located at various places of the campus. The regular way to support that is to have bridges everywhere, because we have virtual LAN, so we should have virtual LAN bridges. And those bridges would talk to each other to build spanning trees, and they would build one spanning tree per virtual LAN. So if you imagine this being done here, all the blue boxes would be bridges, and they would build a tree between each of those. Right? In reality, that's not what is done, because large bridge networks tend to be avoided for lots of reasons, because they use a lot of broadcast, for example. So what is done at places like at the EPFL, you have routers everywhere. Now, how can you route a virtual LAN? In principle, it's impossible. A router is at the layer above. But you can use what is called tunnels. We will come back to the concept of tunnels. It is used, for example, in order to solve problems of IPv6 access. We'll talk about that in a few weeks. But a tunnel is something very simple. It means that if I am this router here, and I am able to communicate with the rest of the network by IP, right? Assume on the edge of the router there is a bridge function that has to handle this virtual LAN. And I also need the bridge part of this blue box to be connected to those 2 other boxes, R7 and R5. One way to do it is to simply use the connectivity I have, which is at the IP layer. So if I have a MAC protocol, a MAC layer packet sent by one source at VLAN 1, for example, it should be sent to another destination which is on the same VLAN. So this packet, ideally, I should pull an Ethernet cable between the two routers and bridge them. But I don't need to do that. I can send traffic from R1 to R7 using IP packets. So I can put my MAC layer frames into IP packets and send them to this line. It's ugly, it does, because it's reversing the order of layers. But this is done to build things like virtual private networks or solve that kind of problems here. This is called a tunnel. A tunnel means we put the MAC packets inside IP packets. Now, if you do that, that solves the problem of connecting R1 to R7, but that doesn't solve the problem of deciding why you should connect R1 to R7, and you probably still need to build a spanning tree on top of your IP layer. I'm proposing to you now, as imagine you are an architect at Cisco, and you have to solve this problem. I'm proposing two solutions to you. What do you think of them? So the majority of you likes A, and a few of you, many of you don't like none of those two solutions. Well, what is clear is that solution B doesn't work. So it's a good idea to use the link state database. After all, R1, if it's a single area, R1 has a view of this. It knows the whole area. Now, R1 knows which VLAN exists on its box. It's VLAN 1 and VLAN 2, the red and the blue. So it can add this information in the topology database. This is not standard information, it's supplementary information that can be added. And by the flooding mechanism, R1 will know that R7 and R5 are in the same VLAN. So this is A. B would not work, because with B, just hearing the MAC addresses doesn't tell you which MAC address is in which VLAN. So A would probably work and would give something like this. Every router knows which of the VLAN it has to support, and also which other routers have to support the same VLAN. And then the routers have to build a spanning tree, because that's the way a LAN works, or at least a distribution tree to send a broadcast, for example. So, but this can easily be done. If you know, for example, R1, you know that R7 and R5 have to support the same VLAN as you, then you have to build a tree. How can you build a tree? Well, at the IP layer, using IP multicast. So you can create an IP multicast group for all the VLAN. Now it's an any source multicast group. And then whenever a source at R1 sends a packet to a destination that is in the same VLAN but at R7, so it's a MAC layer packet, this bridging function in this here will first flood it over the tree, then will learn by reading the MAC addresses that it will learn that it is on this tree, and so it will simply send it here. This has a name. There's two standards that do this. One is called TRIL, another one is called shortest path bridging. So those are things that are done for enterprise networks. This is illustrating how all the building blocks we're using can be used in all the building blocks we have discovered that fit nicely in the layered model of the internet, start to be played together in non-standard way. Here is another question. It's a bonus slide that was not on the slide I posted last week. Here I'm assuming I have 3 boxes and that are bridges or routers, and it's a nice transition to the next topic of congestion control. Here I'm assuming at every box there is transit traffic, lambda packets per second or lambda bits per second, that has to go equally to the 2 other boxes. So there's 50% of the traffic of lambda, the red lambda at A, that has to go to B and C, and the same is symmetric in all the 3 boxes here. I assume the links between the boxes are 1 gigabit per second, full duplex in every direction. And the question is, what's the max value of lambda? which we can interpret as the capacity of this network as seen by every node, A, B, or C. And I'm proposing two options. One, if the three nodes are routers that run OSPF, for example, or if the three nodes are bridges that run the standard things we've seen for transparent bridges with learning of the MAC addresses and the spanning tree protocol. If in those two cases, what's the max value that you think is correct? The majority says B, which is the correct answer. Here is why. The figures on the right are explaining what happens. If we use OSPF in its standard use, we will compute shortest path from every source to every destination. So by using shortest path, the traffic from A to B will go on the direct link. In fact, the traffic from any node to any node will go on the direct link here. If we use the spanning tree protocol with transparent bridges by default, we will have to build a spanning tree of the entire network. So we'll need to, because this is a ring, we will need to disable one of the links. Assume it's BC, then we have transformed this beautiful triangle into a line, which of course has less capacity. And if we do the maths, we see that in that case, the red traffic, for example, is split 50% on each of the links, but the blue traffic, the entirety of the transit traffic coming from B has to go via A, and half of it has to go back to C. So if we look at what is the constraint, what is the volume of traffic that goes in the direction from A to B, remember it's full duplex, so we have 1 gigabit per second in every direction. We have lambda over 2 plus lambda, so lambda. So in every direction and every link, we have lambda, so the max traffic is 1 gigabit per second. Whereas in the other case, it is 2 gigabit per second. So that's the main difference between shortest path routing and spanning tree. In fact, it has nothing to do with OSPF. Any routing method that computes shortest path will have the same property. So if we use distance vector routing, we will have also the same property. So that is, of course, a very important aspect and benefit of having the complexity of OSPF as opposed to the simplicity of the spanning tree protocol. Now let's move to something very popular now. You will see lots of software and topics that have to do with software-defined networking. So let's say a few words about it. It is something very simple and very primitive that goes a bit against the evolution of networking. In OSPF, if you build a network with 200 routers, the only thing you have to do is to configure where the areas are, who belongs to what area. Perhaps also for security, you will need to configure a mechanism to distribute the secrets on all the adjacencies. Once you have done that, the network is automatic. It is dynamic. If there is any change in the network, if there is any failure, the network will automatically adapt to it. And it is completely distributed. There is no central controller that decides where to do what. Another way of controlling a network is to have a central control. And this is motivated by the need to do more sophisticated things in the network. I have mentioned that we can use OSPF to do traffic engineering that is more sophisticated than simply shortest path. We can do even worse things. We can, for example, decide that some traffic has to be subject to some specific treatment. We mentioned that already when we spoke about loose source routing, which is called segment routing in IPv6. Where I had given an example where for some reason an operator may want that some traffic goes via a network node. Loose source routing is a way to do it, but the most widespread way to do it is to use per flow rules and software-defined networking. There is an example that you find in the literature, which is very typical use. Assume you have a network. Those are things that are typically done for huge networks, for the networks of companies like Google, Amazon, Facebook. And assume for some reason you see a flash crowd of traffic coming from a number of sources to one service, which is D1 here. That's the red traffic. Now, because a flash crowd is suspicious, you would like to see whether it's really a very popular service, La Fête des Vignerons, or whether it's a denial of service attack. So what you do in such cases, you use some expensive resources that do deep packet inspection by reading what is inside the packet as much as possible, and use some machine learning heuristics to decide whether this is really something dangerous or it is something that we should accept. So you may want, for example, to send all the red traffic to this special machine that will look at the packets and possibly discard some of them if we decide that this is a denial of service attack. So in a case like this, that means that we need to be able to do special treatment of packets that are not just based on the destination address, because perhaps the blue traffic is going to the same service, that is the same IP, to the same IP address, but not to the same service, for example. So we may want to do per flow decisions on traffic. So in fact, routers can easily do a complement to what we saw. A router normally has a forwarding table that looks essentially at the destination address. You can complement this and add what is called a per flow table. We have seen example of things that we did not call routers, but that many people would call routers, that have a per flow table. What is the example we've seen several times and used in the lab? The NAT. The NAT box has a per flow table. So you can do it in a NAT, you can do it in a router. So in a router, you can add another table, which I will illustrate on this example here. This is showing router R1. It has its forwarding table. It also has a flow table. A flow table is made of 3 columns. A flow specification, that is like a grep search string that says what is the pattern that matches which flows, what action to do on this flow. And now, since there might be multiple matches for flows, we need a way to distinguish which action to apply, or to apply first if there are several. So this is done by using priorities. In the IP forwarding table, there was an implicit way of using priorities, which was called longest prefix match. If there are multiple matches, we give priority to the one that is the longest prefix match. Now the rules are much richer set of operations, so we need to explicitly mention the priority. Here's an example. Assume that in this router, we put those flow rules. What will happen for the traffic from Lisa, who's sitting here, and Homer, that they send to this enterprise server here? And the correct answer is none of the above, because Lisa's traffic will match some of the rules here, input 0 and destination b.d star, so it will go to output number 2. Right. Homer's traffic will not match the first rule, but will match this. So Lisa will match both, but the first one has priority. Homer's traffic will match only the second rule, which means drop, which means that in fact Homer's traffic will be dropped. What are these rules doing? Well, they are essentially saying the only ports, from R1, the only port that is allowed to access the enterprise server is port 0. So only traffic that comes on this port or this interface of the router is allowed to go to the enterprise server. All other traffic will be killed. So as you can see, this is a way of implementing some access rules in a network that are now very specific. Of course, the number of potential rules is very large, so there is a scalability problem if you try to do a very fine-grained set of rules, but this is used in what is called software-defined networking. This originated in big data centers. Google was one of the pioneers in developing this idea. It's a very simplistic idea. It simply means in a big data center, originally it was made for switches, so the same thing that we said for routers applies also to switches. A switch is as a forwarding table based on MAC addresses, but we can add also forwarding rules based on everything we want. IP addresses, port numbers, everything. So, and If you are Google and you have a data centers with 10,000 servers and hundreds of switches, it's painful to go, like we do in the lab, log into every switch and do the rules by opening a command line interface into a switch or a router and give instructions. That's what we do in the lab for small-scale systems. Automating this is what is called software-defined networking. So you have a central controller that will have a supervision of all the switches or the routers and will simply download all the forwarding, all the flow tables in all the switches. This started with switches. Now this starts being developed also for routers, like in the example we gave before with Lisa and Homer. Now you could say, well, this is simplistic, but after all, if it works, why not? So do we still need to study OSPF when we have things like this? What do you think? And the obvious answer is this one, of course. You could say, well, if you have a way to download all the information in the routers or the switches, then that replaces the routing protocol. And this is true in some settings. In fact, originally in the data centers, this is what was done, because in the data center, you have the central controller, everything is in racks inside one room, and you have an out-of-band mechanism. The controller is connected by a special LAN to all the switches. So there's a control LAN that is used to interconnect the central controller and all the switches. If you do that in a more general setting, in a network which has routers, which is presumably larger, its span is not all in one room, but spanning a larger area, the problem is how does the central controller speak to router R1, for example. So SDN uses a TCP connection between R1 and the central controller. This TCP connection needs to have routing tables that work in the routers. So typically, you still run the spanning tree in the case of switches or the routing protocol, for example, OSPF, and then you use SDN to complement or modify the behavior of the standard operation. In the lab, those of you who love that kind of things will have the opportunity to do it as an optional session and see how it works in practice. Voila, that's all for OSPF. More about routing in a few weeks with BGP, and at the end of the course about distance vector. Any questions? Then we move to the next topic, which is a bit different in nature and is congestion control. This is a picture I took during a sabbatical in Paris. You see, what do you see in this picture? Yes, chaos. Nothing else? Well, I see a poor bicycle. Could be me. But I see something else. If you look, the red lights of the cars are on, which means they're all stopped. They all have the brake pedal on. It's an intersection where all cars are stopped. So those cars are stopped. Because they are stopped, they block those cars that want to enter. So they cannot enter. Those ones are blocked by others. So everybody is blocking everybody. Only the bicycles find a way at their own risk through the intersection. This is an example of what we call congestion collapse. The throughput of this intersection, you can measure it and count it in cars per hour, for example. The intersection in the road system is the equivalent of routers or switches in the internet. The throughput of such an intersection is probably a few hundreds or thousands of cars per hour. I'm not too sure about the number, but let's imagine it's 1,000 cars per hour. When there is not too much traffic, if there is more than 1,000 cars per hour that come, then the intersection starts to go into deadlock. It blocks. And then the total throughput is much less because all those cars are blocking. They're not getting out of the intersection. So the total throughput at the peak hour when there's an intersection might go down to 100 cars per hour, whereas just before the peak hour, just before congestion, it was at 1,000. This is called congestion collapse. Congestion collapse is the fact that the throughput, the usefulness of a system, goes down when it is subject to high demand, high traffic. This is not the same as limiting. A good system should not go into congestion collapse. If a system has a capacity of 1,000 cars per hour, it will not be able to have more than that number of cars per hour go through it. If it's a good system, it will stay at this number. Even if you reach a total offered load of more than 1,000, it will be able to do 1,000. So congestion collapse is a phenomenon that occurs in practically every complex system, including us, human beings. If we receive too many mails and too many interruptions, we stop doing much useful work. We mentioned that already in the case of web servers, for example. A web server can be subjected to so many SYN packets that it stops doing any useful work. It's just busy handling SYN packets. That's another symptom, another cause that could make congestion collapse. A web server subjected to a very large number of SYN packets doesn't serve any useful connection. So we will see how this can happen in the internet and what is done to prevent this from happening. The lecture notes for this part of the course are the slides as usual, but if you want a more written text for this part, it's not Olivier Bonaventure's text, but the text that I wrote that is on the Moodle of the course. So congestion collapse happened in '86. So the TCP-IP was built in the mid-'70s. So it took more than 10 years to the internet to discover that actually there was a flaw, a bug in the design, and it was susceptible to congestion collapse. It did happen. And if you look at the numbers, it gives you the historical values. It was observed from Berkeley to Berkeley. And the throughput went down from 32 kilobits per second, not gigabit, right? Kilobits per second, to 40 bits per second. And the reason for that was, well, we will see in a second. So this is also very illustrative of how the internet was built. It was built and see if it works, and if there are problems, fix them when they come. That's very typical of software system. At that time, there were other networks like DECnet and IBM network that did not have congestion collapse, but evolution showed that those networks have disappeared, so it seems that this method of do it first and see if it fixes the problem when they come, was very successful in terms of evolution, at least. Let us see an example that illustrates what the problem is. Here's a small network, which is not very different from how the internet in Berkeley was when the first congestion collapse was reported in the internet. We have two routers, some links. The thickness of the link is about their capacity. So this link is at 1,000 kilobit per second, this one 100, this one 110, 110. And assume I have one source, S1 that sends to destination D1, S2 that sends to destination D2. And those sources are greedy. They use TCP, for example, with very large window size, because the window are given by the availability of the application at D1 and D2, and those ones are not very busy. So the window size is very large, so they send as much as they want. Now, what will happen is, of course, if this one sends at 1,000 and this one at 100, we have 1,100 kilobit per second that want to enter a link that has only 10% of this capacity. So packets will start buffering, and if the buffer is not huge, they will start dropping packets. Let's assume that we ignore the buffering effect, and let's assume that there are losses here. Now you could say if your source S1, it is still a good idea because we know TCP is able to repair the losses. And when we talked about capacity of a path with losses, if you want to maximize the capacity, it's optimal, in fact, to do what TCP does. Send the things, see what goes through. What does not go through, you will repair it. You will send it again. That's, from a selfish viewpoint, that's the best you can do. So let's assume all sources do that. They are selfish. If we do this, what is the rate in the sense of useful rate, the sense of the capacity we saw before, that is sent that is achieved by S1. So S1 sends to D1. What is the rate it will achieve in this network setting? There was a fight between A and C, and the majority says A, which is unfortunately the correct answer. If you said C, you are like Van Jacobson. You believe that by sending at 100 kilobit per second, this is what you will get, because after all, the rest is small. But if we compute in detail what happens, here is one way to approximately see what could happen. At the first link here, at point 1, we have only 10% of the capacity compared to the input traffic. So this output buffer here will need to drop in steady state 90% of the incoming traffic. Now, if this is a fair buffer, which means if you do nothing special, then you will lose every packet with equal probability. So we will accept 10% of the traffic of this guy and 10% of the traffic of this one. So the green numbers are the accepted traffic. So out of the 100 here, only 10 gets through, and similarly here. At the second router, we have two links. At output number 2, there is 10 kilobit per second that wants to go on a 10 kilobit per second link, on a 100 per second link. So everything is fine. The 10 kilobit per second goes through. So that's the answer for us. The rate that's achievable here is 10 for source 1. Now for source 2, we have 100 that goes through here, and here on this outgoing link, the capacity is 10, so we will drop again 10%. So we will have only 10. Right. So the answer is 10% for source 1, but also for source 2. So both sources send at 10 kilobit per second. So we have a total throughput of this network of 20 kilobit per second, whereas if we look at the bottleneck, if we do cut here or there, we see that there was a possibility of doing 110 kilobit per second. This is the cost of anarchy. If everybody is maximizing their own utility, it's better for everybody to be greedy in that case, because you assume the others will also be greedy. Then you get 10 kilobit per second. It's optimal given those rules of the game for everyone, but it's not optimal socially. In game theory, this is called the cost of anarchy. We have a Nash equilibrium, an equilibrium of the behavior of what everybody does, which is not socially optimal here. It is the optimal for S1, because if F1 would send a bit less than 10 kilobit, than 100 kilobit per second, then S2 would get more. So S1 would get less than 10 kilobit per second if it sends less than 100. So it is still optimal for S1 to do that. But that's not good. If we do that in a network, we might have inefficiency. If there would be an oracle, a system that views the global situation, that oracle could say to S1, you can send at 100 kilobit per second, but S2, you should send at only 10. Because that's what S2 anyhow obtains by being greedy. So there's no penalty for S2 to do this. But S1 could send at 100, and if we do that, it works here. So of course, so here we would have 100 for S1 if we go this way. Of course, here I'm doing a very simplified network analysis. I'm ignoring queuing systems. We know that if a link has a capacity of 110, for example, we cannot use it at exactly 100%. So there will be a few percent less, but let's ignore those details here. Now we can see what is the root cause of the problem here. The problem is that S2 was sending too much, because by sending less, it could provide a better fate to S1. And if we analyze what happens is, there are losses at this point here, and the large volume of traffic of S2 causes a large loss to S1. But this is not very useful socially, because a large amount of the traffic sent by S2, which has caused drops to S1, will be lost a bit later. So we have admitted into our complex system units of work that have caused losses to others, but that will ultimately not complete. So that is a symptom, that syndrome of congestion control. That happens in many systems. It happens also in server systems. If you have a server system, like think of a TCP server, if it indiscriminately handles all the SYN packets, then it might be busy accepting a lot of SYN packet, but because it spends so much computing resource on handling the SYN packet, if it doesn't do SYN cookies, for example, that even if there's no attack, that it might be simply busy taking care of opening connection and doesn't have enough resources to do the work, like access the database and do the computation that is required by the application. So the same thing could happen here. You should do that, or you should not do that. And the solution in servers is to have what is called a gatekeeper, have a mechanism that will limit the amount of resources that are given to SYN packets. That is what we will do in networks, but it's a bit more complicated than simply having a gatekeeper. So we have seen so far inefficiencies, but let's go one step further. The network we had before was a feed-forward network in the sense that all the dependency between flows go in the same direction. Flow A interferes with flow 2. That's the end of the story. Here I'm showing a network where there are cycles in dependencies. It's a ring. Of course, no path is a cycle. If you had a path that is a cycle, then the packets would die because of TTL exhaustion. So here I'm assuming traffic goes 2 hops away. It's a very academic example, no, but take it as an example to show, as a toy example to demonstrate the case. I assume at every node there is one source, and the source sends traffic to the node that is 2 hops away in this rotation direction here. And assume the same happens everywhere. Right. So again, so the path of every flow doesn't have any loop, but there are circular dependencies because what source I does impacts what source I plus 1 does and is impacted by what source I minus 1 does. So if I causes a lot of trouble to sources and that itself get in trouble, that will come back into its own phase. So there's a feedback in the interaction here. Let us compute if what is the throughput that is obtained by every source. So in this highly economic example, everything is symmetric. At every node, there is one source that has a rate lambda that goes to 2 hops away. The throughput, so what really gets out, is the lambda second. Similar to the first example we saw a minute ago, we had found 10 kilobit per second for every source. So let's compute the lambda second for every source here. The first thing we can see is that every source uses 2 hop. So on one link that has a capacity C, there are 2 flows that are going. Since all the flows are the same, if the rate of a flow is less than half of the capacity, there should be no loss in this simple model where we ignore queuing behavior. So in other words, if lambda is less than C over 2, on one link there is the lambda of this source, there is the transit lambda of the previous source, the sum of the 2 lambdas is less than C, so there is no problem. The network will not lose practically any packet, and the throughput will be equal to the input. Lambda second will be equal to lambda. This is the non-congested network situation. Now what happens if we go beyond this threshold? Then there will be some losses, because if we are at a given link here, there will be lambda coming in. There is the lambda of the previous one, the lambda prime of the previous hop, that's also coming in. If there would be no losses, those 2 would be equal to the sum of the 2 would be larger than C, which is not possible. So there will be some losses. Let's compute what are these values. So I call lambda prime the amount of traffic of the source that is accepted on the first link, and lambda second what is accepted on the second link, which is also what goes out, because at the exit, there is no contention. Then we have those simple fair mixing assumptions. I assume, like in the previous example, that we drop packets of every input with same probability. The ratio of accepted traffic at one node is, the ratio is what a node can deliver, which is C, divided by what the node has to, what the input. The input is the fresh traffic and the transit traffic here. Okay, we'll interrupt this appropriate moment and see the solution after the break.